Hey there guys, and welcome to your first lab in Physics 3030, which is modern physics. Your first lab is going to be over the Michelson Interferometer, which is this setup that we see drawn here. And the ultimate goal of this lab is going to be to determine what is the wavelength of the light that we are shining into our setup. Let's go over just kind of what this setup is and what all of these components do, and then we'll kind of talk about how we're going to go about finding the wavelength of this laser light. So, initially we have our laser, which is over here, of course, and it's going to enter first through a lens, which is going to disperse or spread out our beam, so it's going to make it easier for us to see our interference pattern on our viewing screen, which is located over here. After passing through our lens, the light is going to pass through what we call a 50-50 beam splitter, and it's called that because it splits the light into a 50% going through the splitter and 50% of it being reflected downwards here. So 50% of the light is going towards our movable mirror M2, and it moves parallel to our laser source, so it moves in this direction. So we can change this distance that we'll call D2 here. So D2 we can change. The other portion of our light that's split goes downwards towards our fixed mirror M, and because it's fixed, of course, that means that D1 does not move, and so D1 is a constant distance. All right, now after bouncing off of both of these mirrors, the light is going to return back to the 50-50 beam splitter and recombine, and then be reflected upwards towards our viewing screen, where we can then see our interference pattern. Now, what is meant by interference pattern or interference in general? So there are two different kinds of interference that we'll talk about in lab: constructive and destructive interference. And we have interference anytime two different waves are interacting with one another. And what determines whether or not if it's constructive or destructive is determined by whatever the phase difference is between our two waves. So let's just go ahead and draw an initial wave here for our constructive interference example. So that should be symmetric about the x-axis, but I'm not a good drawer, so of course it's not. But yeah, we get the idea. So we have our wave. And then we're going to have a second wave that we want to interact constructively with this. And what we mean by constructively is that the amplitudes are going to add together and result in a wave that has a higher amplitude than either of the two individual waves to get by themselves. So when what we want to know is, when is there the most constructive interference, or when are they maximally added together? And that would be whenever they have the same phase. So that means whenever the peaks line up with the peaks and the troughs line up with the troughs, that's whenever we have our maximum amount of constructive interference. So it's either whenever they have the same phase or whenever the phase difference is an integer of the wavelength. And to understand this, you can think of taking a point, any point on this wave, and translating it one wavelength to the right. So if we take this point and translate it one wavelength, it's going to end up again at this point here. If we take this point and translate it one wavelength, it'll end up there, and so on. So you can see all of these points end up at a corresponding point some time later on. Okay, so if I were to draw two waves that had a phase difference of one wavelength or two wavelengths or three wavelengths, any integer of wavelengths, they would just be overlapping each other. So here we have two waves that have a phase difference of an integer of a wavelength, and they look exactly the same. So if we were to add these two waves together, a peak would add with a peak, a trough would add with a trough, and you would get twice the amplitude that you had beforehand. So we can write this, what we call the condition for constructive interference. Our phase difference has to be in lambda. It has to be some integer of lambda, or again, obviously lambda is our wavelength, and n is any integer from 0 to 1. Okay, so let's go ahead and write that down, where n goes from 0, 1, 2, and so on. All right, now let's talk about destructive. So I'm going to start with my same initial wave. And so you can probably guess, if you don't already know, destructive means, if constructive means our amplitudes are adding together, destructive means that they're going to be subtracting. So we're going to end up with a wave that has less amplitude than either one of our two waves individually. And so we have the most destructive interference, where the waves will be completely cancel out if I move each point 1/2 of a wavelength, or if I change the phase by a 1/2 a wavelength. So if we take this point here, we move it over by 1/2 a wavelength, they would end up there. Same thing for this point here. If we move it over by a 1/2 a wavelength, it would end up there. So if we were to draw a wave over the top of this one that's been phase shifted by a 1/2 a wavelength, it would look something like this. So you can see the peaks line up with the troughs, and the troughs line up with the peaks. So if I were to add this point together and this point together, they would add to 0. If I add, let's say, this point and the same corresponding point on the other wave together, that would be, these 2 points would add to 0. So these two waves are completely canceling each other out, so we have a maximum amount of destructive interference. And like we said, this occurs at a half integer. So whenever it's 1/2 of the wavelength. So another way of writing this would be n plus 1/2 lambda, where again, n is 0, 1, 2, and so on. Okay, so now we know something about constructive and destructive interference and what the phase differences have to be between the two waves in order to get each one. So let's talk about what are we going to see on our viewing screen. So whenever our two waves are combining, because we've sent them through this lens, and they're going to be split at different angles, they're going to have a central point in the center where the two waves are going to interact, and we're going to focus on that central point. So for constructive interference at that central point, what we'll see is a bright spot. Okay. And then we'll see, because these waves because this lens diffracts them at different angles, you'll see a portion around this this bright spot that is dark, and then outside of that, there will be another area of constructive interference, and then we'll see another area of destructive interference where it's dark, and then we'll see it be bright again. So it'll look something like this. But again, what we're worried about in this lab is what's happening at the center of these concentric circles. For destructive interference, at the center, the two waves are going to completely cancel each other out. So we'll get a dark region where we'll have nothing, and then we'll have a bright ring around that dark region, and then another dark area outside of that first ring, and then another ring. So it'll look something like this, a series of concentric circles with it being dark in the center. So this is what we'll expect for the destructive case. How am I going to adjust whether we have constructive or destructive interference on this screen? Well, that's why we can move this mirror, right? As I move this mirror, the path lengths of these two different beams are going to change. So where initially the beams are in phase, they get split. And then if this distance d2 is different from this distance d1, then it's going to whenever they recombine, they're going to interfere with each other, either constructively or destructively, depending on what the difference of these two distances are. Right? If they're the same distance, then they're going to combine constructively, and our phase difference will be 0. Right? And so we would see a bright spot in the center. Now, if this phase difference is equal to a 1/2 of a wavelength, right, I would see a dark spot in the middle. So how can we write this in an equation form that relates the difference of these two distances to our phase difference? We'll focus mainly on the constructive difference, because that's what we're going to be looking at in the lab, is we're going to be counting these bright spots. So the difference of these two the difference that the light travels over these two paths is going to be 2d2 minus 2d1. And it's 2 because the light has to travel down and back before they recombine. So whenever they recombine here, the difference that they've traveled of these two branches, we have to multiply by 2 to account for the fact that it goes there and back. All right, so that's the difference of our path length of our two split beams. And that has to be equal to, if they're going to combine constructively, it has to be equal to some integer of a wavelength. If we want to see a bright spot in the middle here, that has to be equal to some integer of a wavelength. So what we're left with here is 2, and if we say instead of d2 minus d1, if we just write that as the change in distance, what we're left with is in lambda. All right, and this is the equation that we're going to use in order to find out what this wavelength lambda is for our laser. So what we're going to do is we're going to move this mirror some distance delta d, and if we count the number of times that this goes from bright to dark, right, so we're counting these number of cycles, which is n, we can then take that information and plug it into this equation and then solve for lambda. So let's see what the graph of this might look like. So if we put this into linear form, where we have delta d as our y on our y-axis, and our x-axis is going to be the change in n here. So actually, this should be the change in n, because it's the change in these two phases that we're counting at different points. So we're looking at the change in n. So if we do look at delta d is going to be equal to lambda over 2 times delta n, where this is our y, where lambda over 2 is our m, and where delta n is our x, if we were to put this in y equals mx plus b form, right? So that means the slope of my line, so that means this is going to look like a line, right? And that the slope of that line is then going to be lambda over 2. So at different counts, it's going to tell you to say, okay, count the 15 cycles and measure the distance over which M2 has to move in order for this to go from bright to dark 15 times. And so if we do that, we'll get 15 and we'll get an average distance and we'll record that. And then it's going to say, okay, maybe I don't remember what the number is, but let's say 30 now. So count 30 cycles and measure the distance that it takes, that this mirror has to move in order for us to see 30 cycles of this going from constructive back to destructive and so on. So you'll count those cycles and you'll get a larger number, and you'll do this for varying counts, right? Taking an average and doing it multiple times, and you'll get a line. And the slope of this line, as we discussed, is going to be equal to lambda over 2. So once you get this slope, all you have to do is multiply by 2, and then that'll give us our experimental value for lambda. And then that is the meat of the lab. Okay, so I think that about explains all the theory that I wanted to talk about for this lab. What we'll do next is I will actually demonstrate using the equipment that you would have used in lab, how you would go about counting these number of cycles, because sometimes it can be hard to see whenever this central area is at its brightest or when it's at its darkest. So what we have to do is use a photometer to measure the brightness of the center so that we can more accurately count the number of these cycles as we change this distance d2. Okay, so let me get this set up and we will be right back. Okay guys, so here we have the Michelson Interferometer setup. You can see here is our laser over here, which is shining the beam through our lens, which is dispersing our, spreading out that laser light. It then enters through our 50-50 beam splitter, 50% of it coming towards our fixed mirror here, and then 50% of it going towards the movable mirror M2 over here. It then again bounces off of those, recombines on the back at the beam splitter, and then it gets reflected towards our viewing screen that you can see on the far end, which are with our interference pattern already there. So everything has already been aligned here. Now, if we want to change that interference pattern, right now we can see that it's interfering constructively at the center there because we have the bright spot in the center. If we change the distance d2 of M2, so if we change the distance by changing by turning this knob, you can see that the center there will alternate between constructive and destructive interference. So constructive to destructive, back to constructive to destructive, and we're going to be counting the number of cycles. So one cycle would be the starting at constructive, going to destructive, and then back to constructive. That would be one full cycle. So we want to count the number of cycles, and then for each number of counts, we're going to measure the distance that we moved M2 in order to achieve that number of counts. And we can do that. We can measure that distance by using this micrometer here. So on here we have different tick marks, and each one of these tick marks is equal to 1 micrometer. And we can actually read between each tick mark as well. You can interpolate, and so the resolution of this micrometer, or for this particular setup, because this has been calibrated for each tick mark to be 1 micrometer, the resolution is going to be 0.1 micrometers because we're able to interpolate between each tick mark. Okay, so that is how the setup works. So we've gotten everything aligned. We can see our diffraction pattern. Now we want to go ahead and demonstrate how you would measure the number of cycles. And so because it's difficult to measure the exact point where the center is the brightest and the dimmest, instead of visualizing it and turning and just doing it optically, what we're going to do is we're going to use a photometer to actually directly measure the brightness. And that's what we have set up at the other end here. So if we move this around now, you can see that our light is going to be going towards this photometer, and the photometer will take the intensity of that light and convert it to a voltage. So the more intense the light is that's striking the center of this photometer, the higher the voltage signal that we'll get. And then we'll be able to visualize that voltage signal by using our oscilloscope on the back table here. Okay, so let's go ahead and do that. So we need to first place this foam over the center, over our photometer, to filter out all of the external light in the room, so that it's now just measuring the light coming from our laser source. And now if we press this button on our photometer, it's going to go ahead and measure the voltage that's being supplied. So you can see a number here. So if I hold that button and then change the distance, so I'm going to go ahead and rotate that micrometer and change the distance D2, you'll see that the number on the photometer will go up and down. And if you're looking at the oscilloscope, you can also see that voltage that we're visualizing on the oscilloscope is going to go up and down. So I'm going to slowly turn it, and we're going to count the number of times that it takes to go up and down. So whenever this line is at its maximum position up here, that's where we have our constructive interference. That's where we're getting our maximum signal. And whenever it's lower, down here, that's whenever we have our minimum signal. So that's where there's the most destructive interference. So this would be whenever there's a dark spot in the center of that interference pattern. So let's do a quick example. We'll start with it at constructive interference, so with it at its maximum. So up around there. And we'll count 15 cycles and then measure on our micrometer what the distance was. So we'll start our micrometer at 0. So we have it lined up. So now we've started the micrometer at 0, and we're lined up at a constructive interference, and we'll go ahead and turn this and count the number of cycles that we get. We'll go ahead and count to 15, I think is the first one that it does. So let's go. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So that was 15 cycles. If we come in here now and look at our micrometer and see where it's ended up at, see if we can get the glare out. You can see this central line here is between the 4 and the 5, and it's almost looks around like maybe 4.6. So our first data point for 15 counts would be 4.6 micrometers. All right, and that's how you would go through this. So you would do that a number of times. You would repeat that a number of different times for 15 counts, and then you would move on to the next number of counts and then repeat it again, getting a distance for each count value. All right, and that's how you would perform this lab. So that data has been taken and provided for you on Canvas, so you can use that data that is on Canvas now in order to complete your lab report, and we will see you next time.